Hello, this is Mr. White, and this video is on volumes of revolution, disk and washer method, part 2. Here are the two exercises for today. Okay, let's get this one off the screen and get to our first exercise. So here we are asked to revolve the region bounded by these two curves around this axis, this horizontal line. Now you notice here that these functions were not given to us in function notation. They were not named for us in terms of f and g, but I certainly welcome you to name them yourself if you feel that is appropriate. So I'm going to do that here. I'm going to rename them f of x and g of x. And you can probably predict that what I'm going to do next is draw a sketch. There's no way we're going to get anywhere with this problem unless we know what we're looking at. So let's start with the f of x. Let's take our basic parabola, or y equals x squared parabola that goes through the origin. There, it looks something like that. And let's vertically shrink it by a factor of 1/2. Okay, there. Now it's at every point it's exactly half as tall as it used to be. And here we'll translate up 3 units. Okay, just like that. Let's now turn our attention to g of x. G of x is simply a line with a slope of 1 and a y-intercept of 7. So we'll draw a line with its positive slope, and I'll extend my f of x curve a little bit so I can clearly see the intersection. We know we're going to want to know where that is. And those are our two curves. Now let's consider for just a moment, what if we were asked to revolve this region about the x-axis? And of course the region I'm talking about is this one right here. If that were the case, then f of x and g of x would give us the radii of this outer volume here. G of x would give us that radius, or those radii, and f of x, without any alteration, without any modification, would give us the radii of this volume here. And we'd end up with a profile that was just mirrored across the x-axis. It would look like this. And we could tell that we would need the washer method because there's this big hole right down the middle of the shape. Okay? But let's now consider, back to the original problem, that we're not supposed to revolve it around the x-axis. We're supposed to revolve it around this horizontal line, y equals 2. So let's take this blue axis and move it up 2 units. Now remember, this is the center line for our solid. So in order for it to stay as a center line, this profile then needs to move up. And it would look something visually like that. And notice that the radii got shorter. The radius to the outer surface, the outer volume, are going to be these line segments here. They don't descend all the way down to the x-axis. The radii of the inner surface, same thing. They've been shortened. They don't go all the way down to the x-axis. Now, how much did all those radii get shortened? Well, they got shortened by 2. So we see from our sketch that it's the g of x function that is going to be the outer volume. So let's write its integral. This will be pi r of x squared dx. And again, I'm just focusing on the outer volume right now. And we just agreed that these outer radii are given to us by the g of x function, but they've been shortened by 2. So we'll put g of x minus 2 in here. So again, outer radius is equal to g of x minus 2. So just to save screen space, let's get this all out of the way and put this in its place. Okay, like that. Now, that was just the outer volume. So let's now turn our attention to the inner volume that needs to be subtracted. This is the volume that we're going to remove from the outer volume. It's the same concept. We're subtracting pi times the inner radius squared, or the integral of that, I should say. And again, let me emphasize, this is being subtracted. And just as we did with the outer surface, we're going to rewrite that in terms of our given function. This time, it's f of x that has been shortened by 2. That's the inner radius. So this little r of x, representing the inner radius, is equal to f of x minus 2. Okay, again, let's save some screen space, move that off, put this in its place. And this is the volume equation for our exercise. Let's give it a little bit of room here, put it all on its own line. So notice that we can tell that this is using the washer method. Remember, the washer method is whenever you have one integral minus another integral. Or at least one quantity, one outer radius squared minus an inner radius squared. But in addition to that, we see evidence of the fact that we're revolving around an axis that was not the x-axis. We see when we have a function minus 2 in this case, and then over here, same thing, a function minus 2, that was the evidence that we are not revolving around the x-axis. Okay, so in all the excitement here, I've been neglecting our limits of integration. We need to find these intersection points, right? So, tell you what, if I bring f of x and g of x onto the screen, I'm going to just trust that if you set this equal to this, that you could solve the resulting quadratic, and you would find that x equals -2 or 4. Okay, so those will become our limits of integration from -2 to 4. And you may notice here that I took what was originally 2 separate integrals, and since they have the same limits of integration, I just combine them into one integral. And for the g of x minus 2, we'll put g of x plus 7 minus 2. And for the f of x minus 2, we'll put f of x 1/2 x squared plus 3, and again minus 2, because that radius has been shortened by 2, just like the other one. Okay, and as I've mentioned in the previous videos, if you were just asked to set up the integral, this is where you would stop and put a box around it. But in this case, let's go ahead and solve, or evaluate the integral. I'll give the abbreviated version. So here I've combined the like terms to give me these expressions, and then FOILed out this expression and this expression to give me the ones on the bottom line. Once in a while we get a little bit lucky. I see that an x squared and a minus x squared cancel each other out. I'm then left with -1/4 x to the 4th plus 10x, and then plus 25 minus 1. Next, we antiderive. Here we go. From -2 to 4, of course, we will evaluate and multiply times pi. And when I plug in that 4, the 3 expressions give me these 3 values. And when I plug in the -2, the 3 expressions give me these 3 values. Time to simplify, and all those fractions combine to 756/5 times our pi. And that is our final answer. Okay, let's go on to the next exercise. Okay, here we have, again, a region bounded by these 3 curves. And that region is to be revolved this time around the y-axis. That's the big difference with this exercise from previous ones. So in the last exercise, I renamed these, or I named them f of x and g of x. I'm going to hold off on any naming for now, and you'll see why in a moment. Let's start by just getting a sense of what these curves look like. Now, this one here is a bit of a strange one. It's not based on any of our basic functions, but x to the 3/2 we can tell that's going to be between our x to the 1 power and our x to the 2 power. So based on that, we'll draw something that kind of curves upward more than a y equals x line would, but isn't quite as curvy as a parabola. There, that's good enough for what we're doing. And then the plus 1 is going to vertically translate it up 1 unit. Okay, there, like that. Okay, y equals 9, that's just going to be a horizontal line here, 9 units up. And x equals 0, that's just the equation for the y-axis. And if we were instructed to revolve this around the x-axis, we'd be focusing on this axis, this center line, and we'd be thinking of line segments oriented this way, defining our radii. Or more specifically, we'd be thinking of these segments as defining outer radii, while these segments define the inner volume radii. But that's not what we've got here. We've got to shift our thinking. We were asked to rotate or revolve this around the y-axis. So let's get rid of this. And envision this rotating around a vertical axis now. This would no longer be the center line. This would be our center line. And the radii of our infinitesimally thick disks are going to be oriented this way. And notice I did say disks. I would like to point out that if this x equals 0 here, if that had been, say, x equals 2, then the border of our region would be moved over 2. And our profile would look like this. And if we revolved it around the y-axis, we'd get something like that. And we would see that, yes, we'd have to use the washer method because we've got a big hole right through the middle of the solid. But that's not what we're dealing with. As fun as that looks, let's put everything back into place and get this out of here. Okay, when we use the disk method, revolving about the x-axis, this was the formula that we used. And I hope you really understand where that formula came from. And if you do, you recall that this dx meant something. It represented infinitesimal thicknesses oriented this way. But notice now that our infinitesimal slices are oriented perpendicular to that. And therefore, we should call them dy. They're infinitesimal changes in the y direction, not the x direction. So this formula needs to have dx replaced with dy for our purposes here. Now, we're still going to have an integral, and the area of a circle is still going to be pi r squared. But instead of looking at our radius as a y value that changes as we move along the x-axis, here I am traveling along x, and the y value is changing. So instead of radius being a function that changes with x, we will now look at it as an x value that changes as we move along the y-axis. So here I am moving up the y-axis, and the x value is changing. That x value is going to be our new radius. So we need to write x, our radius, as a function of y. It changes with y. And as for our limits of integration, we could say that we're going to stack these disks from some y value a to another y value b, but let's just call them c and d instead. Just to make a distinction, we tend to associate a and b with x values, so I'll put c and d to emphasize that these are y values. All right, so what we've got here is our formula for the disk method, but about the y-axis. And again, I hope you look at this as more than just a formula, but as something that you really understand. So let's get this out of the way and apply this new version of the disk method formula. Okay, so as mentioned a moment ago, since we're now looking at the radii here, the radii of these cross sections, we're now looking at those and realizing that those are x values, not y values. They are still going up to this curve. They are still defined by this curve, but we need to rearrange this corresponding equation and get the x value by itself. So if I subtract 1 from both sides, I'll get y minus 1, and then I'll have x to the 3/2 on the other side of the equal sign. And then I'll raise both sides to the 2/3 power and get this expression for x in terms of y. Now, just like in the past, you had the option, if you wanted to write f of x instead of y here, you could. You could choose that name. But if you want to go that route, notice that down here you'd have to call this f of y, because it's expressing x in terms of y, as a function of y. Okay, so a lot of this feels familiar. It just feels like we're flipping everything. All the x's and y's are trading places. And when we now look at our disk method formula, we realize that r of y is the same thing as this f of y. Whether you call it r of y or f of y, or whether you call it x, in either case, in any of those cases, they're just giving us the lengths of these segments, which are our radii. So let's start writing out that formula for this exercise. We'll say the volume is going to be pi integral, and then we're going to put r of y here. That's y minus 1 to the 2/3. And that r gets squared. Our area of a circle is pi r squared dy. And from our sketch, we can see that the little disks are going to stack all the way from y equals 1 to y equals 9. So those will be our limits of integration, 1 to 9. We've completed the setup of the integral. This is where you want to pause if you need a moment to soak all this in. From here, it should be pretty smooth sailing. Okay, so let's rewrite this integral. I'm going to use our exponential properties, which tell us to just multiply those two exponents. That'll give us y minus 1 to the 4/3 power. Let's move this over. This y minus 1 to the 4/3 power can't really be distributed out, but fortunately for us, it can be unchain ruled. If we ask ourselves what's the derivative of that inside with respect to y, unlike our usual with respect to x, we'll say the derivative is just 1. Okay, well, if we wanted to be formal about it, we'll put a 1 on the outside, or a 1 over 1 if you really prefer. Either way, you antiderive that, you're going to get y minus 1. Let's see, that 4/3 is going to go up to 7/3. We'll put a 3/7 out front to balance it out. We'll evaluate that from y equals 1 to y equals 9 and multiply by pi. Okay, I'm going to take this 3/7 and bring it out with the pi. So we'll have 3 pi over 7. Now we'll plug in that 9, and 9 minus 1 will give us 8 to the 7/3. And when I plug in the 1, well, 1 minus 1 will give us 0 to the 7/3, or just 0. We always like it when that happens. Okay, and it just so happens that this 8 is a perfect cube. So when I take that perfect cube, it's 2 cubed, and I take the cube root of it, I'm going to get 2. And when I take that 2 and raise it to the 7th power, we get 128. Okay, minus 0 times 3 pi over 7. And that is going to give us our final answer of 384 pi over 7. It's unlikely I'm going to be doing any videos for the washer method revolved around the y-axis, but I'm trusting you saw that this is basically the same process as revolving around the x-axis, and hopefully you can make that jump on your own.